So in this problem, we're given the lawnmower the mass of its body, mass of each of the four wheels, the coefficient of friction of the ground, the height of a person pushing, desired acceleration, and radius of the wheel. So I'll put some numbers into this. The mass of the body is 50 kilograms. The mass of each wheel is 2 kilograms. Coefficient of friction is 0.7. Radius of the wheel is 0.1 meter. The pushing height is 1.2 meters, and desired acceleration is 1 meter per second. There are some different things we can calculate here. The easiest way for the person is when the lawnmower is doing self-propel. So first we're going to calculate the torque required on the wheels for self-propel. When the person doesn't have to do anything. So then next, we'll calculate if you're using the mower as a push mower, with what force do you have to push to get that same acceleration? And then what happened to me a couple weeks ago is the wheels on my lawnmower just locked up. They wouldn't turn. It made it really hard to cut the grass. And so we're going to calculate for if the wheels lock up, what that force is. So no self-propel, no wheels turning. So in that case, it slides instead of rolls. So for each of these, we'll follow our original procedure. Free body diagram, coordinate frame, equations of motion, and solve. So for one, we'll do torque for self-propel. So if we draw the free body diagram of this, we know that there are four wheels here, and say the weight of the lawnmower pushes down equally on each of the four wheels. So we will just approximate it as a wheel with the box on top. So we will have torque from the wheel. We'll have mg, normal force, and then friction. Now, normally friction opposes the direction of motion. But since the wheel is trying to rotate clockwise, the friction is going to oppose that and go like that. Because the friction has to counteract the torque. That's what keeps the wheels from slipping and allows them to actually turn. So we'll put our coordinate frame on here. Say we've got X going to the side, Y going up. And then we'll write our equations. So sum of the forces in the Y direction equals 0, which equals N minus mg. So N equals mg, and M is going to be total, we need total mass, so that's 50 from the mass of the body plus the mass of the wheels, which is 2 times 4, because there are 4 wheels. And then times 9.81. So this is 567 newtons. Then the friction force, F mu equals mu times the normal force, which equals 398 newtons. Now we don't need to do sum of the forces in the X because we're trying to find the torque here. So we'll just skip straight to torque. Sum of the torques equals I times alpha, which is going to be torque from the lawnmower minus the torque from the friction, which is F mu times radius of the wheel. So there's a couple things we don't know here. Moment of inertia and angular acceleration. We've got to find those before we can find torque. So for moment of inertia, we know for the wheels, I equals 1/2 mr squared for a disc. Say the wheels are discs. And then we'll have to multiply times 4 for 4 wheels. So here I equals 4 times 1/2 times the m, which is 2, times the r, which is 0.1, square that. So that is going to equal, see, these cancel, and we'll have 0.04 kilograms times meters squared. So the moment of inertia here is real tiny. And then, now we don't need to find moment of inertia for the body because the body's not rotating, only the wheels are rotating. Now the angular acceleration, we know A equals R times alpha. So if A is given, then we can get alpha equals A over R equals 1 over 0.1 equals 10 radians per second squared. So now we can plug those things back into down here. So torque equals I alpha. So the I is 0.04 and the alpha is 10. And that equals torque minus the friction force, which is 398 times the radius, which is 0.1. So we solve this out. Torque equals 40.2 newtons per meter. So this is going to be the torque that the engine has to apply on the wheel. So this is total torque, assuming direct drive transmission, total torque on the wheels to reach that acceleration. Okay, so that's the easiest case because the person didn't have to push at all. So now, what if the person is going to be pushing without the self-propel? So we'll draw that free body diagram. Say we've got wheels and mass. So in this case, we've got the person is going to be pushing with a force P at some height H. There's some friction on the ground. And we have mass times gravity going down, and then we have the normal force going up. And then again, the friction has to oppose the rotation of this wheel. So the wheel is trying to rotate like that. So the friction's gonna go against it. We'll have F mu. So because of the rotation, this looks pretty much the same as the one up above, except instead of wheel torque, we've got the person pushing. So the equation for the y is going to be exactly the same. Sum of the force on the y equals 0. So then we get normal force equals 567 newtons. Friction force equals 398 newtons. Now here, we look at the torques. Because there's rotation, we're going to look at this torque. Sum of the torques equals I alpha, which is going to be, instead of torque coming from the mower, we've got the torque coming from the person pushing. So for that case, we'll have P times H, and then minus that friction torque. So then here, P equals I alpha minus F mu R over H, So this is going to be 40.2 over 1.2, which equals 33.5 newtons. So this is push mow force. So 33.5 is really not too bad. So if your mower, which if you've got some friction in your wheel bearings, you know, it could be a little higher than that, but really it's 33.5 is not a crazy amount to push. But if the wheels lock up, we're going to see it gets a whole lot harder. So thirdly, we'll calculate P for the wheels locked. So case 3, if the wheels lock, then they're not going to turn. And so we approximate this as a box sliding along the ground. So in this case, we've got the push, we've got the mg, the normal force, and then the friction has to counteract the push. So friction goes to the left. Now in the y direction, everything is still going to be the same as it was before. Sum of the forces in the y equals 0. So N equals 567 and friction equals 398 newtons. But now, since there's no rotation, we're going to do sum of the forces in x. Sum of the forces in x equals mass times acceleration, which equals the pushing force P minus the friction force. So P equals ma plus F mu, which is going to equal 10 times 1. We had 10 kilograms times 1 meter per second squared, plus the Fu, which is 398. So this is going to be 408 newtons. So 408 is very significant compared to 33.5. So if those wheels lock, the force goes up more than even 10 times.